Okay, so welcome to my talk. Today we're going to be discussing a little bit of the state of C++ modules, this feature that has been discussed for over 10 years, merged in C++ 20, a big improvement in C++ 23, a bit of revising in C++ 26. So what is just the state? What foot are we in with that? So a little bit about myself. I'm Alexsandro Thomas. I'm a senior software engineer. And also, I'm a languages nerd, both programming and natural languages. So if you're into that, please come talk to me. And also, I really like GPGPU. And as part of just trying to do some GPGPU work, I end up stumbling onto some build system work. So that's why I stumbled upon modules. And I thought it was very interesting to try to understand what is the current state of this feature. But I think the biggest question that we need to ask ourselves is, why modules in the first place? Why is this feature required? What brought us to the point where this had to be merged into C++? And for that, I would like to step back a little bit. Let's take a look at a simple C++ program. You just have a main function, a foo function that takes in an integer, returns integer minus 42, and that's one of the simplest programs you can have. Just a function, and when you compile this file, you just invoke your compiler to create an object file, then you link that file into an executable. Very simple. But programmers are creatures that really like organization. So most often what you'll end up with is something like this. You will try to split your files based on logical dependencies and then have multiple files because no one wants a programming file with 1 million lines of code. But here we start to get a problem. Since here you don't have any reference to foo in your main.cpp, you get a compiler error. Your compiler will tell you that foo was not declared in the scope. But of course we can fix that. We can do what is called a declaration that just tells our compiler, trust me, I will provide you some definition for this at a later point at the linker. So now we can use this function. And also if you want to fix the warning for missing prototypes, you can also add it on the other side and everything works as expected. So now if we look at our compilation flow, it will look more something like this. You will have two files being compiled independently, and the only step where both of them are merged together into the executable is when the linker is invoked. So for multiple source C++ programs, you have these source files that you wrote being transformed into this magical concept called a translation unit, which we will come back to soon. Then you know that every name must be declared in every translation unit that it's used, otherwise your compiler doesn't know what you're requesting. The linker will be the thing responsible for finding the suitable definitions, and every inconsistency that you have will cause errors or unintended behavior. And why is that? So let's take a look at an example here. We have our definition and declaration for foo in lib, and then the declaration in main. But let's say that we decide to change our lib.cpp. Now it optionally takes in this extra parameter, so this function is more generic. That sounds amazing. But, well, the problem is, now our linker gives us an error. And the reason is that we're promising to this main.cpp that we will provide it a definition of this function with one argument, but actually we have two, even though it's optional. So you can get a lot of problems by having a system like this. Well, it's not impossible to fix though. You can have what just generalizes this by adding a third file that basically contains this duplicate definition and then requesting your compiler to copy and paste that file into every file that you're using. Well, now everything works as expected, and your compilation flow will look something like this. You have this lib file that is indirectly affecting these two source files, but as you can see, it doesn't really affect the compilation commands. It's just something that your compiler, during compilation time, will load, copy and paste into every one of these files, and everything should work. But then we get into a hairy concept, the one definition rule. We already know that each name must be declared in every translation unit that is used, but any entity must be defined exactly once, and the corollary of this is that only one definition is allowed in only one translation unit. And, well, just to quote Bjarne, the creator of C++, every word in the C and C++ definitions about ODR are there to work around the fact that we cannot identify the one true definition and have to compare definitions instead. So I'm not going to stand here in front of you and try to give you one more definition to compare. I'm just going to try to give you an example. If we have this compilation flow where you have this point header that is used by rectangle and also used directly by main.cpp, and our point just looks like this, you have a struct point, then a rectangle that includes this point, and then makes use by composing on top of this point to create the rectangle class, and then our main.cpp that includes both of these headers and then makes use of them by creating a point and then a rectangle, we can try to observe what the compiler is really doing in this situation. So if we try to observe this file and we try to pre-process it, what is happening here is that the compiler is taking a look. For example, oh, there's a rectangle include. So what it does is just copy and paste that rectangle header. And then it sees that there's a point include. So okay, copy and paste that point include. And this is our translation unit. Whenever you have the total set of your source files merged with your headers, you get your translation units. But then here we have something interesting. If you try to compile this, what will happen? Multiple declarations of point. And the reason is very simple to see in this situation, because you can see that there's two struct points, but it's not as clear when you just have the includes. So it's not a problem that is impossible to fix. Programmers are very clever, and we created a very beautiful syntax to be able to fix this ever since the C days. Isn't that lovely? It's so descriptive. Well, here we're basically just telling the compiler that if this has never been declared before, then, well, do it. Otherwise, just don't do it. But then you might be thinking to yourself, well, but I program in C++. There's something way more modern here. Wow, that is just beautiful. Well, let's pretend a little bit, though. Let's just pretend that our point.h header is now the de facto point header. No other changes needed. There's only one format that is required. It's just perfect. And then we can imagine a structure like this, where you have a program with a main.cpp that has some third-party libraries, but then there's 2 points in which this point lib is imported, both directly by this program and also as a third-party dependency of this mathlib. So if we take a look a little bit at our main.cpp and at this mathlib, we can see that we include mathlib, we include point, and then mathlib also has a pragma once. I mean, we are smart, we can avoid multiple declarations. Well, what will happen here? Everything should work, right? You have a pragma once. Well, compilers don't really seem to agree. Even though this file is exactly the same down to the hash, because they're in different locations, some compilers will not be able to distinguish between them. And that's the case, for example, for MSVC. So it is a little bit of a problem. But, well, some considerations. I'm not here to scare you away from using pragma once. So it's not standard, but it's widely supported. And then the compilers can use some heuristics like the file size, modification time, and file content to try to tell them apart from each other and know that it's the same file despite being in a different path. And also for the header guards, many people say that it can be slow because you force the compiler to invoke the preprocessor on that file. But they can optimize that away. So I'm not trying to scare you away from that, but it is still a problem because, to quote Bjarne again, header files are a major source of complexity, errors caused by dependencies, and slow compilation. Why is that? We can try to take a small look at that. Coming back to our example with the point and the rectangle. This is a very interesting situation, because if we try to remove this include for the point, what will happen? It will compile. And the reason is that we're including point first, so at the moment where this rectangle is evaluated, it already knows about the point. But now, if we switch the order of the rectangle and the point include, what will happen? So this is super fragile. So, and aside from this, I was just trying to understand, okay, what shouldn't be in a header then? Okay, if these headers are this major source of complexity, what should you avoid putting in these headers? Well, Microsoft learned to the rescue. It has some bullet points about things that shouldn't really be on a header. So let's try to break them down a little bit. The first one is a mouthful. Built-in type definitions at namespace or global scope. Well, I don't really understand exactly what this is supposed to mean because it's not very descriptive, but one of the things that it could mean is that aliasing built-in types and headers isn't allowed. Well, that's obvious. If you try to replace, for example, an int with a struct, you will get errors in basically every compiler that this doesn't work, so it's not exclusive to headers. Another thing that is an anti-pattern, or should be, is that if you try to do some defined directives in headers, that can be a bad practice. In this situation, for example, we're defining our integer to be an int64t for the scope of that header, but now we have a problem, because when we include this file in our main.cpp, you actually get a compilation error saying that your main must return int. And that's because when you say int main, you're actually now saying int64t main, even though you never explicitly said that in your main.cpp file. It just transitively propagated. One other thing that this can mean is that aliases can produce unexpected behavior. And if we suppose a scenario where we have our user ID and a product ID just being aliases of int, and then you define this process function that takes in both a user ID and a product ID, now you can have a problem because if you try to use both of these types and then call this function, despite being in the wrong order, your compiler will do nothing to warn you about this. It will just accept this, and you will get an error during runtime. So this weak aliasing is something that might produce unexpected behavior, so don't put it in your header just because you think it's a good idea. Have a good reason for that. Non-inline function definitions are a little bit different. So if we take a look at this lib.h, we have a point struct, this print point function that is defined in the header. So every part of the code is here, and then this add points function that is declared in the header. And then you have our lib.cpp file that includes this header, and then defines this other function that was not defined in the header. And now you have your main.cpp, including this library file, and then making use of these two functions. What will happen if you compile this? This actually compiles fine, because you're providing everything that the compiler needs to be able to utilize these files. But what happens when you try to link this? Now you get a linker error saying that you have multiple definitions. And the reason is that both our lib.cpp and our main.cpp will get a copy of this print point function, because it's defined in both of them now, because you're copy-pasting this definition. Well, it's not impossible to fix, though, in regular C++ either with headers. You could just add inline to this function, or, well, do the right thing and just put it in the CPP file. For non-const variable definitions, you get a similar situation. Your linker will complain to you that there are multiple definitions of variable if you try to link multiple files that have this definition, because every translation unit that is included in this header will get its own copy of the variable, and that's, of course, an ODR violation. Aggregate definitions are a similar concept, which are this type of variables that you can initialize with the aggregate initializer. You get an error from your linker saying that there are multiple definitions of that aggregate variable. That's because every translation unit that includes this header will get its own copy of the variable, and that's an ODR violation. Unnamed namespaces are a little bit of an interesting situation. That's a very common copy-paste mistake when you're moving things from a CPP file into a header to be utilized in other places. But every translation unit that is included in this header will get its own copy of the function definition, as we showed before. And that's binary bloat. It's not really an ODR violation, because you're adding this as something with internal linkage, so the linker will be able to have multiple copies of this function, but it's probably not something that you really want to be copying this definition of this function across multiple files if it could be defined only once. Using directives are also something that can be a little bit tricky, because every time that you do something like this in a header, you're polluting the global namespace of everything that includes this header, even transitively. So that will increase the chance of name collisions if you're doing this with every namespace in your code. So it's something that should be avoided and used only in the translation units properly, not through the headers. So, introducing modules, a novel approach to code organization in C++. And that's not me telling that to you. If you take a look at, for example, Microsoft Learn, they have a note saying that in Visual Studio 2019, C++ modules are a feature that is introduced as an improvement and eventual replacement for header files. So that's a very strong claim. But what are these C++ modules? Well, just to disambiguate a bit, if you've been around the C++ community or C community for a while, you might have heard this name module in different contexts. It can mean, for example, a Clang header module, an Objective-C module, or a standard C++ module, which is what we're going to talk about today. And that can also be broken down into named modules and header units. For the context of this talk, if I don't mention anything, I'm talking about named modules, but we're going to mention both of these. So modules in C++ are just this modern tool for consuming external code from any one translation unit. They just package components and they encapsulate their implementations, and they're designed to coexist but also minimize reliance on the preprocessor, this copy and pasting mechanism that we had before. And it tries to do that by having some fundamental goals, such as componentialization, so that single components are logically grouped, some isolation from macros, so that you have a strict boundary that the macros will not be able to cross, scalable builds by avoiding redundant reparsing of the headers, and also support for modern and semantic-aware developer tools. And that's just because if you have well-structured and machine-readable representation of your program entities, you suddenly allow tools to be able to reason about your code better. And also, of course, reducing opportunities for violating the ODR. So, if you try to imagine some compilation flow like this, like we had before, what we try to conceptually get to with modules is something like this. You just have one file that contains the definitions of your code and the declarations of your code, and then somehow you get this to be able to be utilized by the other parts of your code. And if we take a look at how this actually looks in practice, it would be something like this. If you have this basic lib with a struct point and this add points function, and then this CPP file that includes it, and then does the definition. In modules, this will look something like this. You just say that you're exposing this lib module, then you're exporting this point struct, and you're exporting this add points function. And then you can just have your definitions there, and it will take care of you for not repeating that like it would be done in a header. But every module is actually composed of several module units, as they're called. And they will typically start with a module declaration, so that's how you know that a module is in play in some situation, by having this optional export keyword, module, then the name of the module, and an optional partition name that we'll get to. There are special kinds of translation units, and they're not exposed outside of the module. The only thing that any external consumer of this module has any visibility to is the main module name, the logical name of the module. And they can either be interfaces or implementation units, and they can also be broken down into partitions. It's also important to understand that when all of these module units are compiled, they will generate what's called a built module interface. And what this does is that it provides a very fast access to whatever you were compiling, because it's an intermediate representation that the compiler is better able to parse than a text file. So if we break down this interface and implementation units, it's very easy to distinguish between them, because interface units will have an exported module declaration, and the implementation one will not. So very easy to tell them apart. And for the partitions, it's just basically a tool to allow you to split the interface of modules between multiple files. So for example, if we have this geometry module, we can have this part of the module called circle, and then this part called helpers. You can import the helpers in the circle, and then you can re-export this circle interface into the main module. But so that's where we get to a little bit of a more complicated situation. A module is more like something like this. It's not just one file, but it's actually this collection of files that generates this logical encapsulation, this logical grouping of a component. And then they all get compiled into this precompiled module file that gets utilized, for example, by our main.cpp, and it can also generate an object definition that can get linked, for example, by the linker. So if we do some permutations with what is an interface or an implementation unit, and then also a partition or non-partition unit, we get 4 different types of module units. And if we take a look at that, the primary module interface unit is just an interface module unit without a partition, and every module must have exactly one of these. And that's going to be the most common one that you will see, because you need at least one of these. So whenever you look at a module, you'll probably be stumbling upon this more often than not. Module implementation units are just module units that don't have a partition. And these are very useful tools for splitting the interface or the implementation of your module. And they also implicitly perform import module name. So that this really shows the use case for this, which is just providing definitions for whatever you declare in your module units. A module partition interface unit is just an interface unit that has a partition. And they're just basically tools for splitting large interfaces into multiple files. And they can also, they have to be transitively exported by the primary module interface unit. So you always have to remember that whenever you add any partition, the main file for that module has to remember to expose it to the outside world. The internal module partition units are just partitions that are not exported. And they're basically just useful for utility functions, and they're not part of the external interface of its module. So it's basically just useful for you to break dependencies in your modules and also provide some utility functions in different files. Then you also have something that's called a private module fragment, and they facilitate tidy interfaces. So if we take a look at this function, if you've ever written any type of library C++ code, you know that writing a header is a little bit of an art, because the way you structure it will basically dictate how easily your customer is able to browse through that header file and know what you're exposing to them. But if you have a module like this, that's suddenly a problem, because you have all your code mixed together with all your declarations, and then suddenly very difficult to browse around that. So what this does is it just adds a small field at the end of the module, and it allows you to just move down all of these definitions, all of these header functions into this one single file, while you keep this tidy place where you can just have your declarations so that they're easy to browse. They can only really be in the primary module interface unit, and also they're basically for modules with a single module unit. So they're basically just a tool for you not to have to create two files to be able to get what you do with headers and C++ files right now. The global module fragment is what allows you to use the preprocessor in modules as well. So if we try to do something like this, where we include vector and print in what's called the purview of this module, so the main part of this module, you get an error telling you that including that in the purview of the module appear erroneous. And the reason is that every declaration that you have in this vector and print are now part of your module. You're pretending that they're exported by your module and owned by your module. So if you don't want that, what you can do is just move them up to this small fragment in the beginning of the code. And that will tell you, like, I want to use the preprocessor, but I'm not owning anything here. So now your code suddenly works. And it's important to know that any non-reference entities will be discarded here. So you don't need to worry about including too much and then re-exporting it with every header unit. And it's very useful when it's not possible to import any of the headers. Importing headers? What does that mean? So that's the next part. That's the header units. They basically are a tool that allow you to import a header. And they're translation units that are formed by synthesizing an importable header. Just a note, that's an implementation-defined concept, so I'm in no luck trying to tell you what that means, but, well, good luck. All the declarations here are implicitly exported, so you don't need to go into your old headers and try to export every one of the declarations that were inside of there. You can just suddenly use it. And also they will provide a module-like benefit to your legacy headers that cannot really be converted into a module. So there are some caveats here, though. For example, you cannot really have any external definitions. If you try to do something like this in your header and compile that into a header unit, your compiler will tell you, non-inline external definitions are not permitted in C++ header units, which is actually a very surprising error because it tells you exactly what it wants it to tell you. It's not like 100 lines of templated error code, so fantastic. But you can just easily fix it by just adding inline to this function if you really want to keep it in the header. Also, it's important to note that macros are made visible. So if you have, for example, this define full version and then this full function in our legacy header, and then you have this module that is re-exporting this legacy header, and it has this check version function that utilizes this macro, that will work. But it's important to know that whenever you re-export this header, so whoever is consuming this full module, they will not get access to this full version macro. So there's this strict boundary that only the first importer of anything will get access to the macros, and they will not be repropagated through the interface like they would in a header. And then we get to some very interesting concept that in C++20, the standard defined the concept of the importable C++ library headers. And that's just a tool that allows you to take everything that you had before in your include statements and just transform that into an import statement instead. So you get the module access to everything that was in legacy C++. So that's amazing. But C++23 went a step further and exposed the whole STL as a module. So whenever you had something like this before, you just do this now. You just have replace everything by one line saying import std, and everything that is part of the std namespace will be available to you. You also additionally get this std.compat module that allows you to expose all your C namespace functions. So if for some reason you're using printf in your C++ code, you now can get access to that as well. And also it's important to know that macros are not really exported. So if you need to use something like assert from cassert, you should either import that or include that file. So now we have this powerful tool, but how does it compare to headers? So to look at that, let's circle back to the problems with headers. From a point of dependency completeness, when we had this example before, where we were looking at how it compiles or not, even though it's missing an import there, if we move that to a module, then it's suddenly complete. Your rectangle will be compiled independently whenever point is compiled, and if it doesn't provide any reference to point, it will not be able to compile. In our main.cpp, you can import any of them in any order because you already know that they are logically complete translation units, so they know about everything that they are referencing. And for the problems that are recommended not to put in a header, for example, built-in type definitions at namespace or global scope, when we had this error that we couldn't compile because this define statement was propagated into main. If you move that to a module, you no longer have this problem. This define int as int64t stays local in that module and doesn't get propagated to your main.cpp. For the non-inline function definitions, that's very easy to solve now. You just add export to the beginning of that function, and then it will do what you expect it to do, which is just providing its definition to whoever is importing that. If you have a header that has a variable that we got all of the ODR violations before from using those, just add export, and it will work as you would expect it to. Same thing for the aggregate definitions. Just add export, and now you suddenly have a proper header for that. And the unnamed namespaces are very interesting, because now you can suddenly just move that to a module, and this function will be available in your module unit for you to be able to utilize it as a helper function later on, despite it not being exported. And if you try to export it, actually your compiler will also help you. It will just tell you that you cannot export this, do something simple because it has internal linkage. That's amazing. You suddenly get this checking by the compiler to tell you that you're doing something wrong, instead of you finding out with a very non-descriptive error message by the linker later on. Using directives in the same way, if you move that to a module, this will be available in that one module unit, but it will not escape that module. So now you can just do whatever you want inside of your modules, and it will not propagate. And then there's also something that's really important to note, because there's a lot of talk about encapsulation in C++, both for the purpose of reducing build speed and also hiding internal dependencies. So encapsulation is a tool that's often used. And how it often looks like is something like this. You have these private headers that are being utilized only on a CPP file, and then a user-facing file that actually gets exported to user code. And that can be done, for example, with a pimple idiom, which I'm not going to talk deeply about, but it's a way to break the dependencies. And if you take a look at how that's done in headers, you would have something like this, where you have this secret macro that's being defined, and then this secret function that utilizes the value of that macro. Then you can have this user-facing class that just has this public part of the function that gets exposed to the users, and then some pimple magic to be able to hide all of these dependencies. And then you have your user-facing the CPP file that includes this user-facing header, and this one can actually include and know about this dependency for the private header. So it can now do some pimple magic to be able to get everything working, and then suddenly you can define that public user-facing function in terms of whatever you define with this pimple. With modules, suddenly you get something way more clever, because, well, you can just export this private module, define your secret macro, and then export this secret function. And whenever you are trying to expose this to a user, you just have one file from a module that, well, here you can just expose the user-facing module, import that private directly. You just don't re-export it, and then the users will not know about this dependency. And then you can have all of your user-facing code without exposing your implementation details to any user. But there's a bit of a problem here. This is basically what's happening here. So you have this hidden component, this user-facing component in the user code. But if we try to remove this precompiled header for the private function, so basically just remove it from the disk, MSVC is the only compiler that's really able to do it with one file. The other compilers will still require that build module interface to be there, to be present, even though the consumer doesn't have to know about it. So, well, we can still get around with it, because if you have two module units, one of them that's just the public one and then exposes some details, and then an implementation unit that, well, is able to import private by itself, you can certainly get around this problem. And if you say that you've already seen something like this before, I don't know what you're talking about. For the compile time performance, it's a very important argument, because everyone, when they're talking about modules, are saying that they're faster in terms of compilation speed. So let's test it out a little bit. If we have a hello world program that just needs IOStream, and a mixed CPP program that requires 9 standard headers and just does some operations with some components of all of them, we can have something like this. If we include all of the necessary headers, so include IOStream in the first one and include everything else in the second one, we get compile time performance that looks something like this. And again, don't try to really understand the compile time performance in absolute numbers, but try to take a look at the relative numbers. So, of course, the function that includes more code and does more operations takes longer to compile. That's not really any surprise. So let's take a look at including all of the headers. So just include everything from the standard library. Don't try to save on anything. Just include everything so that you don't have to remember. Now you get a compilation time that looks more like this. So you can see that this is very interesting now, because the compilation times aren't so different. So we start to get a picture of what is really slow when you're compiling any C++ program. If you now have a header that does this instead. You just include everything in that header, and then in your source files, you will include this header instead of everything manually. You get a compilation time that's very similar. Everything here can basically be attributed to some random differences or some small performance difference, because you're basically doing the same operation. You're including every header. If you're importing necessary header units, so just import IOStream for hello world and import the necessary things for mix.cpp, suddenly you get a much better compilation time, because you're not reprocessing all of these headers all the time. You're just doing it once and storing it in an efficient representation that you can just utilize it. And even if you come here and you import all of the headers that are in the standard library, you get a compilation time that looks like this. It's still faster than just including the necessary ones, by including everything and not having to think about it. And if you just put everything here in one header, pre-process this header and include that one instead, it's even better for your compilation time, because everything is in this one file that has this lookup table, and the compiler can know what is defined there and what can be utilized. And then the best feature of them all, import std. You don't have to remember about anything. You don't have to create anything yourself. Just import std. It's available by the standard library. You get this compilation time. And that's really beautiful, because it allows you to do something very powerful for a very fast compilation speed. If you take a look here, importing just one file for hello world makes sense, because, well, there's not a lot that has to be done there. But importing std for mix is actually the fastest option. So even though you get everything, it's the fastest that you can get. If that was for MSVC, for GCC you get a similar compilation time. You can see that importing one for hello world is still the fastest, and importing std is the fastest option for mix. And for Clang, you get this performance. So importing std CPP is actually the fastest for Clang, although not much faster than importing std, but for mix it is the fastest as well. And I can hear some people back in the room talking to their colleagues, but I could achieve this before with precompiled headers or with jumbo builds. But, well, modules are now a standardized feature, and they're accessible by every C++ developer. Every getting started guide in C++ for modern C++ can now provide this as a reference. And also imports are a portable performance gain, which means that any compiler that you put it to, the same code with the same build instructions will have the same compilation performance. And we see that modules really solve some problems. We have now this structured and semantic import mechanism in contrast to that just copy and pasting mechanism that we had before. We have our component interfaces that are compiled independently from the translation units that imported them. You process them only once, and there was an efficient binary representation that made the compilation speeds very fast. And also you had very strong isolation, no global pollution from your macros, because now you have this boundary that cannot be crossed by the macros. But can you really use it? What is the compiler support landscape? Which tools of modules can you make use of for that? And then if you go to some website like cppreference.com, you will see a picture like this. You have partial support for GCC, partial support for Clang, and full support for MSVC. But what does that really mean? That doesn't tell me a lot about which features I can utilize and which ones I can't. So I defined a few features that I wanted to test and just do some feature testing to see, like, can I utilize these features or not? So just to have a note, I didn't go and build any compilers from trunk or anything like this. I just got the latest one from Fedora, which are readily accessible for any C++ developer. So that's Clang version 20, GCC version 15, and MSVC, whatever that number means. So the workflow that I used for testing that is something very simple. You just define a getAnswer function, compile a test for that, and then the test asserts that this getAnswer returns 42. And that will be done for every one of the feature tests. Named modules are the simplest one. You just export this getAnswer function and then test if it works, and every compiler is able to do it. You can just have these named modules, everything will work. Header units are similar. If you just define this 42 macro and then import that into your test.cpp and then try to use this answer, it will work on every compiler. Just Clang is giving you a warning by saying that the implementation of header units is still in an experimental phase, but it still works. Global module fragments are fine. You can import, for example, include CMath and then make use of the sqrt function that you got from the include, and everything will work on every one of the compilers, no problems. Private module fragments, though, if you try to just separate the declaration and the definition of this function, you get an error by GCC, which is the first time in my whole career that the compiler is saying sorry to me and not me saying sorry to the compiler. So that's an amazing error. But, well, the other compilers are able to do it. For the module implementation units, it's basically similar to what we did in the previous slide, but just having different files instead of different parts of a same file. And that is able to be done by every compiler, so you don't lack this feature, you just lack one way to do it. For the module partition interface unit, so just splitting this interface into multiple files. So here we just put this getAnswer function into this partition and then re-export it from that left side. You can get it to work everywhere, that's fine. Internal module partitions also work as you would expect. So if you have this answer function that is a helper and gets utilized by this exported function, every compiler is able to do it. So we get a picture that looks like something like this. That's way more descriptive, in my opinion, than something like what CPP reference shows you. And it shows that headers are almost there. Most of the things can be utilized. So it seems like a bit of fear-mongering to say that everything is just partially supported and, well. So the next part that I wanted to check is standard library modules. Can you utilize these headers and import STD? So if you go to CPP reference again, you also get this very confusing picture just saying that there's partial support for GCC, no support for the STL header units on Clang, but support for the STD module, and also full support on MSVC. But again, what does it really mean? And for that, I wanted to use that mixed CPP file from the previous slides and just try it out, just see what I can get it to compile with. So the first thing that you can do is just define this std C++ header unit that we showed before. So just include everything there, transform it into a header unit and import. And every compiler is able to do it, aside from Clang just giving you a warning and saying that it's still in an experimental phase. But everything compiles, everything works as expected. The STL header units, also if you try to import everything manually, it will work on GCC, it will work on MSVC, but Clang will actually get some problems with that. There are some ambiguous definitions, and it might just mean that I was doing something wrong with the order of the imports or something like this. But again, if it's a feature that's not readily available to be utilized without you having to worry about the order of these includes, then it's not really ready. So I consider this as a failure. And for the STD module, which is the most complicated one and the one that I would expect to be lacking the most on every compiler, it actually works on every compiler. So if you just figure out the compilation commands to get this STD module to work, that's fine, it will work everywhere. And then this is the picture that we get. Clang sadly is the one that's lacking the most behind in terms of having these features readily available for you. But the best feature that is this import STD is actually available everywhere, so you can start to play around with it. But there's a caveat here. For the standard library, they basically agreed by now that the users have to build their own BMIs. And just because different versions of the compilers and different options will provide different representations for these built module interfaces. So you just have to remember the commands to compile that. So which, for example, is this for Clang, it's this for GCC, and it's this for Clang, for MSVC, and you don't have to remember that. You can just access the slides later and take a look if you're interested. And it's also important to note that compilers don't really seem to agree on what these modules features should look like. So even the file names, I was utilizing the Clang convention all the way until right now, but MSVC treats the module interfaces as this .ixx file that gets compiled to and .ifc. GCC is just a regular C++ extension that gets compiled to these GNU compiled modules files. So the compilers don't really seem to agree right now on the format or the ABI for all of these things. So they all differ between different compilers, and that means that you cannot really utilize them across different compilers. If you build a module interface with Clang, you cannot utilize it with GCC and vice versa. And even on different versions of the same compiler, you might not be able to utilize them. And also you introduce a lot of very strict consistency requirements. For example, the compilers as of right now, they require you so that your compiler options will be the same. So your C++ dialect has to be the same, your optimization level, your macros and some of the compilers have to be the same. Your source files have to be the same, which is something very important because they are not a way to hide implementation details as of right now. You just have to, you need to provide all of the source files that were used to build a built module interface alongside with the module that is built. Or you can just embed that source code together, so you cannot just build something and ship that built interface to a user that you don't want to have access to your source code. You also have this object definition consistency, but that's actually a good thing because that just means that it can now, because it's a semantic import mechanism in the compiler level, it can check across different of these translation units if there's something duplicated or something like this that might cause a problem in the linker stage. But what's the stage with build systems and tooling? I don't think that anyone here is compiling their C++ by hand every time, so what can we do here? And the biggest problem is that now we need build ordering. And that's something that exists before. So let's take a look at something like this. If we have a lib geometry that has a point, a rectangle, a square, and a circle, and then your main function, your main source file, and you have a rule that main utilizes this lib geometry, you get a compilation graph that looks like this. And I know this looks intimidating, but you can actually logically group these things. You just have your headers on the left side, and they don't really directly impact anything in the compilation stage, but they are there, and they're utilized by everything. Then you have your sources that can be compiled independently, because you're just including all of the source files from the headers, and everything is just being duplicated, so there's no reason to order these compilations. And the only thing that actually has to be ordered is the binary linking, because all of the source files for this library need to be present when you're compiling this libgeometry.a, and this libgeometry.a needs to be present when you're compiling main. And that's what's called an embarrassingly parallel build, because everything can basically happen in parallel. You're just duplicating the actions that would need synchronization, basically. And with modules, you get something that looks a little bit more like this directed acyclic graph. You need to resolve the dependencies first before you can build, because you need the product of a build step to be able to import one of the modules in the next one. So it's, in my opinion, a little bit easier to reason about, and also at the same time that you're not being able to do everything in parallel, you're not repeating actions, and I don't really like my CPU just repeating actions for no good reason. So things are a little bit more complicated now when you think about builds, because now you need to scan these dependencies. So if you have, for example, this simple square module that just exports this rectangle include, and we can discuss if square is a rectangle later, but what we need to do is basically just scan the dependency. So the compiler can create a file like this for us if we invoke it, that just says, whenever I compile this file, that will be my primary output. That's what you can link to. I will provide this logical component called square, and you can import it by making use of this square.pcm file. And I require this logical name called rectangle. And then this can be used by our build system to basically synchronize all of these build actions. And you can do that, for example, in CMake by doing something like this. In CMake 3.28, you have native support for named modules. Just a note, this is basically only supported on Ninja and Visual Studio, so RIP makefiles. And also, they don't really support header units, but they do support name modules. And how you do it is basically just specify your minimum version required. You set your C++ standard to 20, because, I mean, modules need that version. Create a project, add the library, and then cast some arcane conjurations to be able to add this as a source file. So there's this very weird new syntax that's called like a file set. And there are some plans to expand this so that everything can be defined in terms of these syntax, so that it doesn't look so odd just for modules themselves. But that's how you have to do it right now. You just have to tell the compiler or the build system that this is a module file and not a regular file. And then in the end, it's just treated as a library, so you can add your main executable, link to that library, and CMake will be able to do that. And if we inspect how this build works, it goes something like this. First, it will scan all of the CPP files to know what modules are needed and what modules are exported. Then it will generate these dynamic dependency files and then build the objects in the right order that they have to be built. And then just link, like always. And you even get experimental support for this import std functionality. And the way this works is that you just have to specify this very weird character string that you need to dive into the CMake documentation and source code to be able to find. So it's not really a production-ready feature, but you're able to start playing around with it. So you just paste it in there, enable the std module on, and then whenever you add your executable, you just add your executable. You don't even need to tell CMake that you want to utilize std. And the way this works is that CMake will inject a lot of steps into your build to just deal with that std module first, and then resolve your normal program in the way that it would usually do. But that's a little bit interesting, because we don't really just use a build system by ourselves, and we are not writing every library that we utilize. So we want some type of dependency management. And dependency managers already perform a lot of very important features for C++. For example, automatically retrieving and fetching, integrating libraries from remote repositories. also doing transitive dependency handling by pulling in the dependencies of your dependencies. Then it enforces cross-platform consistency by getting the same set of libraries working on multiple compilers, multiple systems, and everything like this. You have your build integration that just like many of your tools will hook into your build system to be able to provide a very easy access to whatever you're utilizing from those libraries, so that you can just utilize them without having to worry about also providing build system support for them. And they also provide binary caching so that they speed up the builds by just building the libraries once and allowing you to reutilize them. And if you think about what the build system or dependency manager has to do for modules, it's more of the same, but even more on these 3 steps, because now you need to make sure that these intricate build module interface files will work across your different systems. And there are 3 ways, at least conceptually, that can happen. One of them is to just wrap your non-module library code with an adapter. So for example, the FMT library, you could just fetch your FMT library, build it like always. The dependency manager is already able to do that. Then you as the consumer, as the developer, you maintain this fmt.cpp file. Then you compile this header unit, this module that you make yourself, and you can now suddenly import FMT. The option 2 would be for the compiler for the dependency manager to do it themselves, because you might be thinking to yourself, but FMT is a library that already supports modules, and that's true. So what you could do is, for example, just fetch that library, build it as normal, but also expose this module file that is inside of that source. But the problem as of right now is that none of the dependency managers that are popular, like VCPackage or Conan, will do that for you. So even though the library does support modules, it does not do this functionality for you. So you have to do it manually if you really want it. And the third option, which would be the best option for a developer and for a consumer perspective, is just ship the pre-built built module interfaces. And how that would work is that you would just fetch the FMT library, compile the module inside of the dependency manager, and as a consumer, you just say import FMT. You don't have to worry about any of the files that were part of that library. You're just worried, I want a module. Dependency manager, please do that for me. But again, if none of the dependency managers even support option 2, that's a little bit difficult that they would do that. And that it's understandable, because this process can easily become very platform-specific, very difficult to maintain, and also very error-prone. So many developers are not really doing that right now, because better first-class support for these tools would be greatly supported by the developers. Because, well, in a very, very scientific approach, I think I had this experience when I was using this type of approach, because even to get to the first option with a dependency manager in C++, you already get a lot of headache. But then as you try to go up this nice to use functionality, you just get a bit of a headache. But you have your project. Can you really adopt modules right now? What is the outlook for that? Well, many of the tools are now recommending you to just start with modules. For example, Clang is saying it is best for new code and libraries to use modules from the start if possible. Or Microsoft Learn saying that we recommend that you use modules in new projects rather than header files as much as possible. And there are some very good advantages for that, because if you adopt modules early, you minimize the transition cost later on. And also any future improvements will be easily achievable because you're already utilizing modules. And it's easier to structure your code for having modules in the first place if you start like that. But for existing projects, the choice is not always so clear, because most projects will not really just rewrite everything at once. You have this middle time where you have both your headers and your modules at the same time. Then you will need to increment your build system support, and you will need to get all of your custom developers in your company to also learn this new feature, which I think might be the most difficult point. And also you should be aware that there are other build time strategies that might be better suited for your project at this point. So you should take a look at precompiled headers and Unity builds. You should also really investigate if header units can be utilized, because they provide modern access to your legacy headers in your system, and then there's no code change required. You can just use them as they were and import them instead. But there are some problems, like it's still experimental in some of the compilers like Clang. There's a lack of build system support, so you cannot really utilize them, for example, with CMake, and every macro-heavy header will end up breaking because of these boundaries for the headers that are exposed. So basically the best approach that you might have right now is just to do incremental adoption. Just start slowly with some utility libraries in your code, and then try to move to some self-contained components. Gradually start converting some commonly used headers into your modules. you should try to experiment also with internal-only modules before you expose any public ones, because at the moment that you start exposing a module, you basically force all of your customers to also utilize modules, so that might not be something that they want to do right now. You should also have some very strong code guidelines for using modules, and always be reviewing your build performance metrics, because it might not make sense for you to utilize them and have all of that effort to move to them. And for a future and current outlook of modules, they were introduced in C++20. C++23 came with enhanced module support, because now you can just import std. And C++26 has some further replacements to improve the tooling support. But we're still not quite there. If you take a look at this picture, which is a mandatory picture in any modules talk, you just have this information that we're basically going to be finished by 2297, which I don't think I'm going to be alive to see that. So unless it's speed up, well, we're not really in a good picture with modules. And that stems from some adoption challenges. It's kind of a chicken and egg problem between users and tooling, because if you go talk to tooling maintainers, for example, Conan, they will just tell you, no one is asking us for it, so we're not prioritizing that. But also the users are not really prioritizing using modules because that's not there, it's not present, it's not easy to utilize. The compiler and build system support is kind of uneven, so it's really difficult for you to get into the ecosystem right now. And also there are libraries that rarely will publish modules, so most of your libraries, you will not really get this module interface access, so you might not bother to try to utilize modules a little bit more in your project. And also you get things like your build module interface is not really being portable. So they're really difficult to utilize as of right now. They're not an information hiding mechanism, so that's not even a redemption point, and you cannot share them between compilers. But it doesn't have to be like that forever. All of your BMIs could be shipped independently. Your shared libraries could be type safe and self-descriptive by just embedding a build module interface in a shared libraries, and you can reason about what is there without also externally shipping a header. You could also enable foreign function interfaces. You could have a world in which Python or Node could open up one of these build module interface files and just directly hook to the functionality. You don't need to suddenly use like PyBind or any other wrapping functionality just to be able to utilize your C++ code in any other programming language. And also, you could have cross-compiler compatibility appearing, so suddenly you could utilize BMIs for maintaining a stable ABI across compilers that they could use to communicate from. And you do have many interesting things that are coming. For example, you have the fact report that clarified that preprocessor definitions don't affect importing the headers. You have a paper that forbids macro expansion in the name of modules, so tools can more easily know the name of a module without having to scan that file. You clarify how you can use main in different module units, or how you cannot. And also you have some papers that are doing some very nice work about providing some ABI requirements or some consistency requirements that would help you shipping these modules alongside your C++ libraries. But so you can see that the ecosystem is developing, it's not static. And you also have some refactorialized improvements that can happen, because if you read from the standard in cpp.include, it says that the implementation can treat importable headers, which again, implementation defined, as if they were actually an import. So you can see in the future maybe some build system trying to come across in the future and just replacing all of your includes automatically with imports. So maybe everyone in the future will be able to benefit from the speed and the practicality of modules without doing any change to their code. So a question is, what is the future of C++ now? We do have a new baseline. The C++ modules do shape the future of C++ because they provide real encapsulation alongside build improvements that are very noticeable. They provide standard important semantics that no longer just work based on a hack that is copy and pasting declarations from another file into your program. You have easier boilerplate and migration for any new developer or old developer that just wants to start off with some guide or something like this. And you can also have that AI can now generate module first code because this was merged into the standard. This is standard C++. So whenever you go into your ChatGPT in the future, for example, and you ask how to create this in C++, it can already suggest you to do import std in the future, which will give any new developer trying to learn C++ a great experience by just doing that and not having to remember the name of every one of the headers that correspond to the functions. So, well, in my opinion, are modules the future of C++? Absolutely, yes. They're shaping the way that C++ is coming to be by just providing these semantics about importing foreign code. Are they the future of your current project, though? Maybe. This is something that is an individual decision that I think everyone has to take a look at their current project to try to decide for that, but I hope to have given you enough information to decide that and maybe you want to try it out. Thank you. Any questions?
If no one has a question, I have a question. You show some error reports, like compiler tells you what's wrong, but you mostly were showing MSVC. What about REST? Are they also so helpful with their error messaging?
In Rust? Oh, not the REST, sorry.
With GCC Collab. Are they the same helpful as MSVC?
They are. There's one thing that most of the standard says that for these features, no diagnostic is required if you make something wrong, but most of the compilers, at least the ones I tested, seem to give you a very helpful and descriptive error message. MSVC actually seemed to be one of the ones with the best error messages, but all of the compilers do seem to have them.
In one of your slides, I saw anonymous namespaces in header files. Was that just for demonstration purpose, or are there any use cases where you should do that?
Yeah, so the question was about anonymous namespaces in headers, and I think that that's not something you should do. That's actually an anti-pattern. You shouldn't really be doing that. But the thing is, it's a very common copy-pasting mistake, because if you have a CPP file that has some functionality, and then you're porting that to be able to be utilized outside of that one CPP file, you end up copy-pasting whatever is inside of there and moving it to the header. And then if you had something in your anonymous namespace for that one CPP file, well, that just goes to the header, right? And then you get that problem that you can end up including it in multiple files and you get binary bloat, so nothing is really going to fail, but you can have problems by doing that.
What happens when you do the namespaces when you do import FTD, for example? Does that also input the namespace as well, like using STD?
Yeah, so the question was about what happens with the namespaces, for example, when you're importing STD. And for the STD module itself, yes, whenever you import STD, you get everything in the STD namespace, so you get the namespace available for you. But it's not part of the module definition that they automatically provide you the namespace. So for example, in Python, if you do an import, you have to do like the name of the module, dot, and then the feature that you want. That is not the case with C++. You would need to remember to do it yourself. So if you create, for example, a module called lib, it's a very nice thing if you remember to wrap everything there in a namespace lib.
Okay, so you have to do it manually.
Yes. You have to do it manually.
Yeah. Makes sense.
That's it. All right, thank you very much.